I'm going to explain about complex reaction. These are the types of complex reactions I have written: reversible reaction, consecutive reactions, and parallel reactions. First, let me explain about reversible reaction. Reversible reactions where the forward and the backward reaction rate will be equal. That is the reversible reaction. As the reactant is converted into product, when the product concentration reaches certain amount, then the product will combine to give back your reactant. So as the product concentration increases, then the rate of the reverse reactions also increases. So at certain time, the forward and the backward reaction will be same. So the net rate of the reaction will be 0. So as the reactant converted into product, then the product will combine to give back your reactant after some time, at certain given in a given time in this, or after some time, then the forward and the backward rate will be equal. So the net rate will be 0. Net conversion will be 0. Here ethyl acetate hydrolysis is given as an example. See, I'll take A is converted into product. We say this is a reversible reaction. A is converted into B. The forward reaction rate constant is K1, and for the reverse reaction the rate constant is, let me write, K inverse. At time 0, then the reactant concentration is A, product concentration is 0. At time, after some time, let me say T, the product concentration is X and the reactant concentration is A minus X. The unreacted molecule will be X. So K1 is actually the rate constant of the forward reaction, and the K minus 1 is actually rate constant of the reverse reaction. So therefore, here now I'm going to write about rate expression for the forward and the rate expression for the backward reaction. So the rate of forward reaction is, we say, D in terms of X, in terms of product concentrations, I'm writing dx by dt is equal to K1 and A minus X. This is the rate of forward reaction, and the rate of reverse reaction is dx by dt equal to K inverse and X. This is rate of reverse reaction, this is rate of forward reaction. See, the rate of forward reaction is actually, rate of forward reaction is dA by dt equal to dB by dt. This is how we define rate, equal to K1 concentration of A. So at time t, the concentration of a unreacted molecule is, concentration of A is A minus X, and the concentration of B is X. Therefore I write dx by dt equal to K1 and A minus X. That's what I have written here. This is a rate of forward reaction. And for the rate of reverse reaction, rate of reverse reaction is, for the reverse reaction, this is product is your B is your reactant. For the reverse reaction, B is your reactant. Therefore I'll write it as D, concentration of B by dt is directly proportional to concentration of B. Therefore K inverse and B. So therefore this is dx by dt equal to K inverse concentration of B at time t is x. This is what I've written. This is concentrate. This is rate of your reverse reaction. So this is rate of forward reaction and this is rate of reverse reaction. And the net rate of the forward reaction will be given by net conversion, forward reaction and reverse reaction. If the net rate of the reaction in the forward reaction, the forward direction is in forward direction is given by, let me say, dx by dt equal to dx by dt forward, the rate in the forward direction, minus dx by dt, the rate in the reverse direction. This will give the rate of net rate of the reaction in the forward direction. So that is written as dx by dt equal to dx by, sorry, it's already written. This is k1 a minus x minus k inverse x. So this is the net reaction in the forward direction, net reaction rate in the forward direction. So next I'd like to explain about consecutive reactions. Here you see consecutive reactions are, say, a multiple step reactions. A reaction involves in multiple steps. Is an example, will be an example for consecutive reactions. Let me say A is converted into B and the B is converted into C. This is a consecutive reaction. Here I have written two steps. For this step, for the first step, let me write the rate constant is K1, and for this step the rate constant is, let me say, K2. And for here time at time 0, let me say the concentration, the initial concentration of the reactant is A, and the concentration of B is 0, and concentration of product C is also 0. And concentration at time t is, here let me assume it is x, it is y, it is z. At time t, the concentration of A is x, and concentration of B is y, and concentration of C is z. If K1 is actually greater than K2, that is the K1 value is larger than K2, then the first step will be faster than the second step. In other words, the second step is slow step. If K1 is very large compared to K2, then the K1 is actually the first step will be very fast, and then the second step will be very slow. We know that the slow step is the rate determining step. So the rate of conversion of A to C is determined by the step 2. So the steps 2 will be your rate determining step. And on the other hand, if K2 is greater than larger than K1, K2 is very larger than K1, then the first step will be your slow step and the second step will be your fast step. So the rate of this reaction is determined by the first step. The slow step is your first step. If okay, let me write the rate of the rate of first step, or the rate of disappearance of A is again rate in terms of A minus dA by dt is equal to minus dx, because the concentration of x at t is concentration of A at time t is x. So minus dx by dt is equal to rate constant into concentration of A. That concentration of A at time t is x. So this is the rate of disappearance of the reactant A, and the rate of formation of C is given by B. The rate of formation of B is given by the formation of B, the rate, because the concentration of B increases when the concentration of A decreases. So I'll write the rate of formation of B dB by dt. Here you see here a positive sign is given by dy, because at time t the concentration of B is y. So dy by dt is actually given by K1 x minus K1 2y, K1x minus K2y. Then what is that? K2y is actually rate of formation of C. The rate of formation of C. So the rate of formation of C is given by the change in concentration of C with time is given by concentration of C at time t is z dz by dt is given by rate of formation of C is given by in the second step the C is formed. Therefore K2 into concentration of B actually disappears. I'm writing the rate of the step 2. Rate of steps 2 is actually d change in concentration of C by dt. The concentration of C is z, so that's why C concentration of C is written here z, and then this is directly proportional to K2 into concentration of B. Concentration of B at time t is y, so K2y. So the rate of formation of B is given by this equation, because in the first step this is formed, B is formed. In the second step the B is disappeared. So the rate of formation of B is given by the rate of the first step minus the rate of second step will give the rate of formation of B. And if you plot time versus concentration, and time, if you plot time versus concentration, then you will see this curve, that is A is converted into B, B is converted into C. So when A is converted into B, the first step, and B, the second step, B is converted into C, the concentration of A actually decreases at 0 time. This is your concentration of A. So the concentration of A is actually decreases. Then when A concentration decreases, then it produces concentration of B. Therefore, the concentration of B, as the concentration of A decreases, when the concentration of A decreases, the concentration of B will increase. As the concentration of B increases, then the B started giving molecule C. So the C concentration slowly increases. So after some time, you'll notice the concentration of B decreases. Concentration of B will decrease. And concentration of C, at the beginning, the concentration of C formed will be smaller, and then after some time the concentration of C will go up. So this is the plot of concentration versus time for a consecutive reaction. Next, let me explain about parallel reaction. Here the example of consecutive reactions, you see any reactions which involves more than one step is an example of a consecutive reactions. Parallel reaction a molecule A simultaneously gives a product B and C. This conversion, so molecule, there are two products are formed in the same time. So A is converted into B as well as A is converted into C. That is, more than one way this reactant reacts to give product. See, let me take, this is K1 is the rate constant of this conversion, and K2 is the rate constant of this conversion. Here say the example, I'll write an example here. The phenol is nitration of phenol will form ortho and para product. Ortho nitrophenol, and the product, the another product is para nitrophenol. So is an example of a parallel reaction. The rate of let me say for this conversion, the rate, the change in concentration of B is given by K1 and A, because the formation rate of formation of B, or rate of this conversion in terms of B, change in concentration of B with time, is directly proportional to concentration of A. And for this conversion, the rate of formation of C is equal to K2. So the overall disappearance of A overall rate of disappearance of A is given by minus GA by dt equal to the rate of and this step plus rate of this step K2 and concentration of A. If you take the ratio, of these two equation, you will get K1 by K2. The rate of this step and then the rate of this step, if you take the ratio, you will get this equation. And by using these two equations, this equation and this equation, you can find out the rate constant value. This is parallel reaction.